So 7.5, we'll be talking about solving, quote, harder trig equations. Now, I put the word harder in quotes because they're really not more difficult. It's just not as straightforward or plain as the problems we saw in 7.4. Remember, the whole point of 7.4 is just to get us used to and accustomed to the idea that solutions to trig equations are infinite due to the cyclical nature of angles. I really wanted us to practice getting a feel for the idea of plus pi k or plus 2 pi k. So 7.5 will be devoted to more the algebra side of the solving. What type of techniques or skills or little methods do we need to know in order to successfully manipulate trig equations? Now, we did talk about a couple of ideas and hints that we can use back in 7.4, and they were these trig equations are going to be a lot easier if your trig functions are the same. If your entire problem uses only cosines or only sines, then we have some things that we can use to tackle that. If you have like sines mixed with cosines, mixed with tangents, those are typically what I call hard problems. Now, if your problem does come mixed, with sines and cosines and everywhere, the idea is that you need to use algebra and or trig identities to make all the trig functions the same. Once all the trig functions are the same, it's just an algebra question. Yes, it might use sines and cosines, but the idea is use good old-fashioned algebra, be it factoring, inverse operations, square rooting, squaring, whatever you need to do to isolate the variable. However, the new thing that I'm sort of injecting today is that all these hints and tips and techniques and special methods, they go all out the window if you only have one trig term. If your entire problem only has a single sine or a single cosine or a single tangent, I don't care how crazy or complicated that trig function looks, if you only have one trig function, then it's just straight up regular algebra, inverse operations. You don't need fancy identities. You don't need fancy techniques. And we'll see an example of that as we come on. So there really isn't anything new to learn in terms of concepts in 7.5. It's just exposing us to different algebraic techniques, exposing us to different solutions. So that's what the whole purpose or the whole basis of today's notes will be, just taking a look at a handful of examples. So let's take a look at this example here. Suppose it asked you to solve 1 plus sine theta equals 2 cosine squared theta. So this is a, quote, hard question because it violates the first bullet points. The trig functions are not the same. We're mixing sines and cosines. Well, think back to to the first half of Unit 7. I see a cosine squared. I see a trig function being squared. I also notice I have a sine here, and knowing Pythagorean identity, I know that we can transform cosine squares into sines. So that's probably the way we should go. So we're just going to straight up use Pythagorean identity. We should know that cosine squared is 1 minus sine squared. And then you distribute. And yes, it's still a, quote, hard problem because we have multiple trig terms here, but at least they are all the same. We recognize one of them is being squared. We recognize we have a singleton. Maybe this might be quadratic. Well, to solve a quadratic equation, it needs to equal 0. So we're going to move everything onto one side. Let's go ahead and add the 2 sine squared, and at the same time, let's subtract the 2. So that gives us 2 sine squared theta plus sine theta, and if I subtract the 2, it gives us a minus 1. And lo and behold, what do you know? This problem is factorable. 2 sine, this is just what we did yesterday. And then we want a positive 1 in the middle, so I need a plus 1 here and a minus 1 there. So the zero product property says 2 sine theta minus 1 could equal 0, or sine theta plus 1 could equal 0. So the left equation gives us sine theta equals 1/2, whereas the right equation gives us sine theta equals -1. Now for the left equation, the reference angle, what angle has a sine value of 1/2, is going to be pi 6. Since it says sine theta equals positive 1/2, I know that sine is positive in the first quadrant and in the second quadrant. So reference angle of pi 6 gives us actual answers of theta 1 is pi 6, and theta 2 is, what's that, 5 pi 6. Now, the right equation, we have sine theta equals -1. So that's going to be a special quadrantal angle. And knowing that math is done on a unit circle, I know that sine is negative down here. So this right here, because this has coordinates 0, -1, I know that 3 pi halves is a solution to the right answer. So technically we have 3 separate answers: this angle here, this angle here, and this angle here. But I want to see if I can't merge them together. So right now we're sitting on 3 separate statements. Is it possible to merge these guys all together into one? I honestly don't know until I draw it out. So let's draw all of our answers onto the same coordinate system. So we have one answer here, one answer here, and one answer. No, I'm going to switch to pink. I think that has a wider brush. Yeah. And one answer here. So certainly it looks like it visually, but again, these are just sketches. These are approximations. I can't know with absolute certainty that these guys are all equidistant from each other. So let's just do a little bit of math here. So this is pi 6. This is pi 6. Well, if this is pi 6 and this is pi 6 and the whole guy is 1 full pi, you have a 6th here, you have a 6 here, you have 4 pi 6 left over, or in other words, 2 pi thirds. 4 pi 6 reduces to 2 pi thirds. So know that this right here is 2 pi thirds. And what about this part over here? Well, I know that this is a right angle, so that's pi halves. In terms of denominator of 6, though, so I know that this is 3 pi 6, which ends with this being 1 pi 6. I know that the whole angle here is 4 pi 6, or in other words, 2 pi thirds. And lo and behold, this is 2 pi thirds as well. Right? So while it looks like we have 3 separate statements, because these 3 answers are actually equidistant to each other, we can actually blend our solution into one giant statement. So what this means is I can start at any solution. Let's say I started at the yellow solution. Instead of going 2 pi 2 pi radians to get to my next answer, I only have to travel 2 pi thirds to get to the purple answer. And then from the purple answer, I just have to travel 2 pi thirds to get to the pink answer. And then from the pink answer, I only have to travel 2 pi thirds to get back to the yellow answer, so on and so on and so forth. So instead of yellow plus 2 pi, purple plus 2 pi, and pink plus 2 pi, I can just say that my answer is pi 6, which is the yellow answer, and then I'm only going to travel 2 pi thirds k, where k is an integer, to reach all of my other solutions. Right. So this is an example where, you know what, our 3 separate answers are all nice, neat, in one package. So there you go. That is a pretty cool problem. I didn't actually expect that. I didn't do these problems beforehand, so that's a pretty cool thing that happened there. Let's pick another random example. Say, sine of 2 theta minus cosine of theta equals 0. I hope it's very obvious to see that, hey, I got a sine here and a cosine here, so they're different. Also, the angles are different. I got a 2 theta here and a 1 theta. So that's just like the double whammy. Not only are the trig functions different, but the angles are different as well. Well, think of all the identities that we learned in the first half of Unit 7. Well, clearly, this is 2 theta. This is a double angle. So I'm going to use a double angle formula for sine. So looking at my reference sheet, or because I know it, I know that sine of 2 theta is 2 sine cosine. So that's what we can actually do. So I'm going to write down 2 sine theta cosine theta as a trig substitution for the double angle for sine. And then, of course, we have the minus cosine equals 0, and then we can factor out the cosine, and then it becomes like a regular problem that we did yesterday. Right? As a matter of fact, this might be the same example that we did yesterday. So zero product property, cosine of theta equals 0, 2 sine theta minus 1 equals 0. So sine theta equals 1/2. So we already did this one in the previous example, right? Sine theta equals 1/2. Yep. So I know, I'm not going to go bother with the whole reference angle business. I know that my answer is going to be pi 6. And then my other answer is going to be 5 pi 6. That's because it was from the previous example. Now cosine is 0. 0 is special. So I know that I have one answer at 0 radians. And I have another answer, I'll do this in a different color so we can differentiate. I have another answer at pi radians. Right. So if we put it all together on one coordinate system, we have one answer here. We have one answer there. We have one answer there. And then we have one answer there. Now, I don't have to do the math. I can just do by visual inspection that these cannot be blended into one statement. There's no way that this angle is the same thing as this angle is the same thing as this angle, which is the same thing as that angle. So I can just forget about blending this together as one statement. But I hope everyone can see that the yellow and the pink answer are symmetrical, right? They separate this circle into two halves. So instead of having two separate statements for the yellow and the pink, I can just have one statement going from yellow to the pink. My thing froze on me. Okay. I can have one statement from the yellow to the pink, and then from the pink to the yellow. But unfortunately, the purple answer and the red answer, they're not symmetrical with each other. So that one we're going to have to do as two separate statements. So altogether, we should have three separate statements: the yellow statement, the purple statement, and the red-orange statement. So what is our answer? Let's start with the yellow statement. Theta equals, well, this is 0 radians, so I'm not going to even bother writing 0 radians or 0 degrees. Well, I guess I'll show it to for the purpose of the notes. 0 plus pi k, because we only need to go pi to reach to the next answer. Now, on the answer key, they will not write the 0, so they'll probably just write pi k. And then for the purple answer, that was pi 6 plus, again, since the purple was not symmetrical to anything else, we're going to have to go a full circle to get a next answer, 2 pi k. And then for the red answer, that was 5 pi 6. And again, the red answer was not symmetrical to anything else, so you're going to have to go a full circle to get you to your next solution, plus 2 pi k. So that would be the complete solution to that example. Let's see here. Oh, this one is pretty neat, this example here. This highlights that you might have to depend on algebra rather than trig identities. So suppose I asked you to solve this equation, and they're going to tweak the instructions in the interval 0 to 2 pi. Notice that they say, I only want answers in this interval, and I hope everyone can recognize that this interval is one full circle. When you see instructions like this, that means they don't want a general solution. You don't need to do the plus pi k business. Just make sure you write down all your answers within one full circle. So that's actually easier for us. So what makes this problem special? Well, notice we have two different trig functions, so that makes it, quote, hard. But there's nothing really going on here. There's no squares, so I can't use identities. The angles are all theta, so I can't use half angles or double angles. So this one, it seems like we are, out of luck. What can we do? The technique in this case here, if you only have one sine and one cosine, is just square both sides, right? Isolate the sines and cosines, put the sine on one side, put the cosine on the other, and you just got to square both sides. That's exactly what we're going to do first. Now, you got to be careful. Squaring is not an invertible operation, or in other words, x squared does not have a true inverse. So we may produce extraneous solutions. All this means is, I guess I'll write this down. If you square to solve an equation, you must check your answers. Because it is possible to start with a false statement and end up with a true statement when you square things. So that's why mathematically you just have to check your answers whenever you use this technique. So the left-hand side becomes a cosine squared plus 2 cosine plus 1 equals sine squares. And then what can I do? I still have a problem of having sines and cosines together. Now, it looks like we can use Pythagoras' identity. We have a cosine squared and sine squared, but they're on opposite side. It only works if you have cosine squared plus sine squared, and then we're going to have to subtract something, so that's not going to work out. Maybe we can... Well, we got more cosines than we do sines, right? So I'll go ahead and do Pythagoras' identity, but I'm not going to use it with the cosine squared and the sine squared. I'm just going to use it with the sine squared because that will at least bring everything in terms of cosine. So let's go ahead and do that. I think that's the right route. Cosine squared theta plus 2 cosine theta plus 1 equals, and we should know that sine squared is 1 minus cosine. Okay, I see where this. So this is nice. This is good for us. Everything's in terms of cosine, so let's just bring everything onto one side. So we'll go ahead and add the cosine squared, and we'll go ahead and subtract the 1. So that gives us 2 cosine squared theta plus 2 cosine theta, and then if we subtract the 1, the 1's cancel out, right? So now we can factorize everything. We don't have a trinomial anymore, so this is not a regular quadratic. So let's just do the greatest common factor. We can pull out a 2 cosine. And then the zero product property says 2 cosine theta equals 0. Cosine theta plus 1 equals 0. So you get cosine of theta equals 0. Cosine of theta equals -1. Now, 0 and -1 are special. That means they're quadrantal angles. So if I look at the coordinate system, that means my answer is pi, because that's where cosine equals -1. And my answer is going to be pi halves. That's where cosine is 0. And 3 pi halves, because that's where cosine is also 0. Now, I don't have to worry about symmetry and all that fun stuff, because the problem says we want to stick in one circle, so I don't need to worry about multiple answers. But we did, so let me go ahead and write this down. Theta equals pi halves, pi, 3 pi halves. But we did square both sides of the equation in order to solve this at the beginning. And this is what the algebra technique says. You must check your answers if you're going to use this technique. So you have to take your possible answers and plug into the original problem. And our original problem was cosine theta plus 1 equals sine squared. So let's go ahead and just check them. Let's check theta equals pi halves. So you just plug into the original equation. Plus 1 equals sine of pi halves. And then you just evaluate. Since these are actual angles, you can just figure it out. Cosine of pi halves is 0. Sine of pi halves is 1. You get 1 equals 1. So this is a good answer. So this is good. Let's check pi. So you get cosine of pi plus 1 equals sine of pi. Cosine of pi is -1. Sine of pi is 0, so you get 0 equals 0. So that's a good answer. Let's check theta equals 3 pi halves. So you get cosine of 3 pi halves plus 1 equals sine of 3 pi halves. That is -1 plus 1 equals sine of, what's that? Oh no, cosine of 3 pi halves is 0, excuse me. That's -1. You get 1 equals -1, which is not a true statement. So you actually have to throw this guy out. Our original problem only has 2 answers. Right? So the moral of the story of this example is check your answers. Let's do one more example. Let's do an example where the angle is pretty funky. Suppose I ask you to solve the square root of 3 tangent of theta over 2 minus 1 equals 0. At first blush, everyone's probably going, oh, I know how to do this. It's the half angle. So we're probably going to use the half angle formula. And that's totally A-okay. If you want to use the half angle formula, mathematically, it is not wrong. But the thing I want us to focus on here is, notice, we only have one trig function, right? We have a single tangent. Anytime your problem is just one trig function, throw all of your special identities, throw all your special tricks out the window, just solve it like a regular equation. Get the theta by itself. So we're going to add 1 to both sides, divide both sides by radical 3. So now we've isolated the trig term. Now, we can, even though this is a half angle, I'm going to sort of like ignore it, right? I'm going to pretend that it doesn't exist there. So maybe, I don't want to use a different color because you should write this down. But I'm going to think, once you isolate the trig term, once you isolate the funky angle, don't think in terms of the funky angle. It could be theta over 2, it could be 5 theta, it could be theta squared, or it could be whatever it is. We're going to do a variable substitution. I'm going to think x as theta over 2, right? So now, therefore, I'm solving tangent of x equals 1 over radical 3. So that should be pretty easy for us. This is a basic trig equation. So, okay, oops, didn't want to scroll down. What is the reference angle? What angle has a tangent value of 1 over radical 3? That's going to be, what is that, pi 6? What quadrants is tangent positive in? Well, it's in the first quadrant and the third quadrant. Pi 6 here. I'm not going to bother figuring out the other angle. We already know he's symmetrical, so there's going to be one statement. So I hope everyone can agree that x equals pi 6 plus pi k. That was not too hard of a question. But our original problem wasn't in terms of x's. No. Our original problem was theta over 2. So all you got to do is substitute that back in. Instead of x equals pi 6 over pi k, it's therefore theta over 2 equals pi 6 plus pi k. And then you just go ahead and solve for theta. I hope everyone can see that you just multiply everything by 2. So theta equals, if I multiply everything by 2, what's that? Pi thirds plus, I guess I'll show my work. 2, that is pi thirds plus 2 pi k. There we go. We solved it. So yes, typically whenever your angles are funky, that usually means use a special identity or use some sort of other technique. But if you only have one trig function or one trig ratio, just use normal algebra. And once you get towards the end of solving, just do a variable substitution. Whatever your funkiness is, just call it x and then solve it like normal. So hopefully these gives you more perspective, more techniques, more methodologies under your belt in order to tackle these trig equations. Only way you can get better at this is if you practice. So good luck. Have at it.